In 1687, Isaac Newton published the Principia Mathematica and fundamentally changed how humans understood the universe. He showed that the same mathematical laws governing falling apples also governed the motion of planets and stars circling in cosmic dance. For over 2 centuries, this classical framework seemed complete, unshakable, built on bedrock that nothing could shake. The universe operated like an intricate clockwork mechanism, a vast machine wound up at creation and running down according to eternal mathematical laws. If you knew the position and velocity of every particle in existence at any given moment, you could theoretically calculate the entire future with perfect accuracy and reconstruct the entire past without ambiguity. Determinism reigned supreme. Reality was predictable, mechanical, and comprehensible through mathematics. Laplace's demon, a hypothetical intelligence with complete knowledge of the present state of every particle, could know everything about the future and the past. But as the 19th century faded into the 20th, experiments began revealing cracks in this beautiful, orderly machine that had seemed so perfect. Measurements that shouldn't behave strangely started behaving impossibly strangely. Light refused to obey Newton's predictions for how waves should behave. Atoms emitted radiation they shouldn't emit, according to any reasonable calculation. The universe, it turned out, was far more alien than anyone had imagined in their deepest physics. We stand at the threshold of that revolution, about to journey into the quantum realm where reality operates according to principles that transform the meaning of knowledge itself, where particles exist in superposition, where observation shapes existence, and where the ancient dream of perfect prediction dissolves into fundamental uncertainty written into the laws of physics. You're about to discover how physicists were forced to reimagine the entire fabric of reality itself from the ground up. For 300 years, classical mechanics reigned as the undisputed king of physics. Newton's laws explained everything from the trajectory of cannon fire to the dance of celestial bodies across the night sky. The classical world was a deterministic universe where cause directly led to effect in chains of perfect causality. Every phenomenon could be broken down into smaller pieces, examined in isolation, and understood through mathematical relationships. This worldview offered something profoundly satisfying to the human mind. It suggested that reality was fundamentally knowable, that reason and observation could unlock nature's deepest secrets. The universe operated according to fixed rules that never changed, never wavered. Light was a wave propagating through a medium called ether. Matter was composed of indivisible atoms that collided like tiny billiard balls, following trajectories determined by Newton's laws. Energy was a smooth, continuous quantity that could take any value. You could have a tiny amount of energy or a huge amount, with infinite gradations between them. Nothing prevented smooth transitions. The laws of thermodynamics described heat and energy in perfect mathematical terms. Electromagnetism unified electricity and magnetism through Maxwell's elegant equations. By the late 1800s, prominent physicists spoke confidently about wrapping up their field. Lord Kelvin declared that physics was essentially complete, with only minor details remaining to be worked out. The future seemed to offer only refinement, not revolution. Classical mechanics gave us certainty, predictability, and a sense of rational control over knowledge. If you understood the initial conditions precisely enough, you could predict any future state. The past was equally accessible through calculation. Nothing was fundamentally unknowable in principle. This offered tremendous psychological comfort. It suggested that reality, while complex, was ultimately transparent to human reason. The deterministy worldview became the foundation of science itself, the bedrock upon which all scientific knowledge supposedly rested. If you could measure the position and velocity of every particle in the universe at any given moment, you could theoretically rewind time backward or project forward infinitely far into the future. The universe became a cosmic clockwork, operating according to laws as precise and predictable as any machine. Mathematical laws gave science power. They allowed prediction and control. Engineers used Newton's laws to build bridges and cannons. Astronomers predicted planetary positions centuries into the future and tracked them with precision that seemed almost magical. This success of classical mechanics bred confidence bordering on arrogance. Many physicists believed the fundamental questions were essentially solved. Further research would merely fill in details and extend calculations to ever more complex systems. Scientific instruments became increasingly sophisticated. Measurements grew more precise. The experimental arsenal expanded dramatically. Spectroscopy allowed researchers to examine light in unprecedented detail. Microscopes revealed cellular structures never before imagined. Yet with every improvement in measurement capability, physicists encountered phenomena that violated classical predictions. Atoms emitted light in discrete colors rather than continuous spectra. Metals released electrons when illuminated, but only if the light's color exceeded a certain threshold. Heated objects glowed with intensities that shouldn't exist according to mathematical predictions. The classical framework that had seemed so complete, so final, began cracking under the weight of experimental contradictions. Scientists couldn't ignore these anomalies. They couldn't explain them away as measurement errors because the effects proved reproducible and consistent across different laboratories and different experimental conditions. The universe was telling physicists something profound. The rules they had trusted completely were incomplete. Reality operated according to principles they hadn't discovered. The classical illusion, so comfortable and satisfying, so mathematically beautiful, was beginning to crumble at its foundations. The clockwork universe was showing itself to be an approximation, valid only under certain limited conditions, failing catastrophically at scales where atoms and light danced according to different rules. By the 1890s, physicists faced a crisis that shook the foundations of their discipline. Blackbody radiation presented the first major problem. When heated objects emit radiation, classical physics predicted that hotter objects should emit increasingly intense radiation at shorter and shorter wavelengths. According to classical electromagnetism, radiation should intensify without limit as wavelength decreased. This meant that the total energy emitted should approach infinity. But experimental measurements showed something completely different. The actual energy distribution peaked at a specific wavelength and then decreased as wavelengths shortened. The universe refused to obey classical theory's predictions. Physicists called this contradiction the ultraviolet catastrophe because it predicted infinite energy at ultraviolet frequencies where experiments clearly showed finite energy distributions. The prediction wasn't merely off by a small factor, it was catastrophically, fundamentally wrong. The mathematics should have worked. Classical physics had successfully explained countless phenomena, yet at ultraviolet wavelengths, the equations that worked perfectly for long wavelengths completely broke down. The classical answer was literally infinite energy, which clearly never happened in nature. Something was profoundly wrong with the theoretical foundation. The photoelectric effect added another puzzle. Physicists discovered that when light struck certain metals, electrons were ejected from the surface. This seemed straightforward enough from a wave picture perspective. Brighter light should transfer more energy to electrons, yet the details contradicted everything classical physics predicted. The kinetic energy of ejected electrons depended on light's frequency, not its intensity. Brighter light should knock out faster electrons, according to classical physics. Instead, the frequency mattered exclusively. Below a certain frequency, no electrons emerged no matter how bright the light illuminating the metal. A dimmer blue light could eject electrons that intense red light couldn't touch no matter how many photons flooded onto the surface. Above that threshold, electrons emerged with speeds determined purely by frequency with remarkable consistency. The energy of ejected electrons scaled linearly with frequency. Double the frequency and you doubled the electron's kinetic energy. The classical wave picture of light couldn't possibly explain this behavior because waves were supposed to accumulate energy. More intense waves should transfer more energy. Doubling light intensity should double the energy transfer. Instead, it only increased the number of ejected electrons, not their speed. Something fundamental was wrong with the theoretical framework that had served physics so well. Physicists watched experimental result after experimental result contradict their theoretical predictions. Max Planck studied blackbody radiation intensely, trying to make classical formulas match experimental data. For years, he attempted various mathematical tricks and theoretical modifications. No matter what he tried, classical mechanics failed. The mathematics simply refused to work. He discovered that if he assumed radiation could only be emitted in discrete packets, multiples of a fundamental energy unit related to frequency, the mathematics suddenly worked perfectly. The experimental curves matched theoretical predictions with remarkable accuracy, but this violated everything classical physics stood for. Energy couldn't be quantized. It had to be continuous, like water flowing from a faucet, capable of taking any value. Yet the mathematics demanded quantization inescapably. This desperate measure worked and produced accurate results because it acknowledged something revolutionary about nature. The universe might not be smooth and continuous at small scales. It might be grainy, digital, composed of indivisible packets of energy. A particular frequency of light would always carry the same energy packet. You could have one packet or two packets, but not 1.5 packets. This granularity at small scales challenged everything physicists believed about the smooth continuity of reality. Albert Einstein extended this radical idea to explain the photoelectric effect. He proposed that light itself consisted of discrete particles, photons, each carrying energy proportional to frequency. This contradicted the wave picture of light that dominated physics for over a century and had proven phenomenally successful at explaining diffraction and interference patterns. Yet it explained the photoelectric measurements perfectly. The energy of a photon depended only on frequency. Brighter light simply meant more photons, not higher energy per photon. This explained why brightness didn't affect electron ejection speed. Only frequency mattered. Niels Bohr applied similar ideas to atomic structure and achieved tremendous success. He proposed that electrons orbited nuclei in discrete energy levels, not the continuous range of orbits that classical physics predicted. An electron could exist only at certain specific distances from the nucleus corresponding to specific energy levels. An electron could jump between levels by absorbing or emitting specific amounts of energy corresponding to discrete frequencies of light. This discrete atomic structure explained atomic emission spectra completely and precisely. Each element emitted characteristic colors of light because electrons jumped between specific allowed energy levels unique to that atom. The lines in hydrogen's spectrum corresponded exactly to energy differences between Bohr's allowed orbits. Red, green, blue, violet lines appeared at exact frequencies matching the energy difference calculations perfectly. Classical physics predicted atoms should emit continuous spectra across all frequencies as electrons spiraled into the nucleus. Nature showed something completely different, and Bohr's discrete model captured it. Scientists confronted an uncomfortable truth. The universe refused to behave classically. At the smallest scales, reality seemed to operate according to completely different rules. The measurement crisis deepened as researchers probed atomic phenomena. Classical physics suggested that atoms could have any energy value, any electron orbit radius. Nature disagreed fundamentally. Atoms exhibited discrete properties, stepping between specific states rather than occupying a continuum. The deterministic continuous universe of classical mechanics was showing itself to be a profound illusion. A radical transformation of physics began around 1900 and accelerated through the 1920s. Max Planck's desperate attempt to fix blackbody radiation theory inadvertently opened a door to an entirely new physics. His assumption that energy comes in discrete packets seemed absurd at first, a mathematical trick rather than a description of reality. But the results proved impossible to ignore. Planck himself was deeply uncomfortable with his own discovery. He spent years hoping someone would prove him wrong, that the quantization would prove unnecessary. He tried to recover classical mechanics by assuming that energy quantization applied only to emission and absorption, not to radiation itself. He hoped that reality at a fundamental level remained classical, that his quantum concept was merely a calculation aid. But the experimental evidence piled up relentlessly. Einstein's explanar. Time of the photoelectric effect required treating light as genuine particles carrying energy in packets. Bohr's atomic model required discrete energy levels that electrons occupied without spiraling into the nucleus, as classical physics predicted they should. The building blocks of a new physics accumulated piece by piece, despite decades of resistance from established physicists who couldn't accept that determinism and continuity had failed. Young physicists began thinking differently from their elders who clung to classical certainty. Instead of trying to fit quantum effects into classical frameworks through mathematical tricks and reinterpretations, they asked whether nature operated according to entirely different principles at small scales. They began to accept the possibility that reality bifurcated at a fundamental level. At large scales and everyday temperatures, the classical picture worked wonderfully, giving us bridges and airplanes and planetary mechanics and all the technological successes of the industrial age. At atomic scales, where particles moved in confined spaces and possessed tiny energies comparable to Planck's constant, completely different rules applied. The classical laws of physics that governed rolling balls and falling objects and spinning planets simply didn't govern electrons in atoms. This shift in perspective proved revolutionary. It required intellectual courage to accept that classical physics, so successful and beautiful, was merely an approximation valid only under certain conditions. Most established physicists resisted this conclusion violently. But the younger generation saw something the older physicists couldn't. They saw that accepting two regimes of physics was far more truthful than denying experimental evidence. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed mathematical formalisms that captured quantum behavior with stunning precision. Schrödinger's wave equation described how quantum systems evolved over time. Heisenberg's matrix mechanics provided an alternative formulation yielding identical predictions. Dirac unified quantum mechanics with special relativity. These new theories made predictions that were confirmed repeatedly by experiment with accuracy that continuously increased as measurements improved. Yet, unlike classical mechanics, quantum mechanics didn't describe reality directly. It described probabilities, possibilities, states of knowledge rather than definite facts. The entire structure of the theory rested on this probabilistic foundation. The state postulate emerged as the central concept of this new framework, the foundation stone upon which all quantum predictions rested. The state postulate asserted that quantum systems could be fully described by a mathematical object called a quantum state, often represented as a wave function, typically denoted by the Greek letter psi. This state contained complete information about the system. Complete information didn't mean knowing all facts about the system in the classical sense. It meant knowing all that could possibly be known in principle about the system. A complete quantum description specified everything about the system, but what it specified was radically different from what classical physics meant by complete description. A classical description of a particle told you its position, momentum, and all other observable properties. A quantum description told you something much more abstract and subtle. But crucially, the information was probabilistic in nature. The quantum state didn't tell you the definite values of observables like position or momentum. Instead, it specified the probabilities for different measurement outcomes. If the wave function told you the probability of finding a particle at different locations, that represented complete knowledge even if the particle's actual location remained uncertain before measurement. Before you measured the position, the electron didn't have a definite location. The wave function specified a probability distribution. That was all that could be specified. That was all that existed to specify. Upon measurement, the wave function collapsed to a definite location drawn from that probability distribution. When you measured a quantum system, you didn't passively read off a predetermined value that existed somewhere in reality before measurement occurred. The measurement process itself determined what value you would find, drawn from the distribution of possibilities encoded in the quantum state. Before measurement, the system existed in superposition, a mathematical combination of all possible states weighted by their probabilities. The act of measurement revealed one possible outcome from the many possibilities, collapsing the superposition of states into a single measured value. The measurement outcome was determined by probability, not by hidden predetermined facts. Different measurements of identically prepared systems would yield different results according to the probability distribution unspecified by the wave function. This represented a profound break from classical physics that disturbed many physicists. Classical states specified definite properties existing independently of observation. Quantum states specified only probabilities that became actualized through measurement. The universe at fundamental levels didn't have definite values for all observables simultaneously. Reality was genuinely probabilistic at its core. Measurement didn't reveal pre-existing facts, it generated facts through interaction. The State Postulate transformed the meaning of physical knowledge completely and irreversibly. To know a quantum system completely meant knowing its wave function, knowing the probability distribution for all possible measurements. It didn't mean knowing what position a particle occupied right now. That was unknowable in principle, not through experimental limitation but through fundamental necessity. Perfect knowledge of a quantum system meant accepting inherent uncertainty about specific observable values. This represented the most radical reconception of knowledge in the history of physics. Classical physics identified complete knowledge with knowing all observable properties definitively. Quantum mechanics identified complete knowledge with knowing probability distributions. These were incompatible definitions. One or the other had to be wrong. Experiments proved that quantum mechanics definition was correct, and nature actually worked that way. The universe had transformed from a deterministic machine to a probabilistic process governed by mathematical laws of a completely new type, laws that even their discoverers found deeply troubling. In 1924, de Broglie proposed something extraordinary that challenged the very foundations of physical thinking. If light could behave as both wave and particle, why couldn't matter? Why couldn't electrons, protons, atoms exhibit both wave and particle properties? This suggestion seemed impossible to most physicists. Particles and waves seemed fundamentally different categories of physical phenomena. Waves spread out, oscillate, interfere with each other, produce diffraction patterns. Particles are localized, discrete, definite, follow trajectories from one place to another. How could the same thing be both? Yet de Broglie showed mathematically that if you assigned electrons a wavelength inversely proportional to their momentum, the resulting wave picture could reproduce experimental atomic spectra perfectly. The shorter wavelength corresponded to faster electrons, just as classical intuition suggested. Electrons, it seemed, possessed wave-like properties alongside the particle-like properties. Davison and Germer performed an experiment that confirmed de Broglie's hypothesis directly and unambiguously. They fired electrons at a crystal surface and detected an interference pattern identical to what you'd get from diffraction of classical waves passing through a narrow opening. Electrons diffracted like waves. They showed interference patterns. When electrons passed through a crystal lattice acting like a diffraction grating, they produced patterns of constructive and destructive interference. Yet when measured individually, electrons arrived as discrete particles hitting a detector in localized spots. You could never detect half an electron or fractional electron energy. Each detector registered a complete discrete event, a quantum jump from one state to another with no intermediate values. Wave-particle duality suddenly seemed fundamental to nature itself, not a temporary confusion that further investigation would clear up. This wasn't a measurement limitation. This was how electrons actually behaved. The double-slit experiment, originally performed with light centuries earlier, took on new significance in quantum mechanics and became the quintessential demonstration of wave-particle duality. When you send electrons through two slits simultaneously, they produce interference patterns indicating they somehow traveled through both slits as waves. The two electron waves interfere with each other, creating bands of high probability where the waves align constructively, and bands of low probability where the waves align destructively, probability where they interfere destructively. But if you install a detector to catch the electron as it passes through one slit, it chooses one slit or the other with certainty. The interference pattern vanishes completely. Where the two slits should have created bands of constructive interference, you now get a simple pattern like throwing classical balls at two holes. The act of observation changed the behavior fundamentally. When observed, the electron acted like a particle going through one slit only. When unobserved, it acted like a wave going through both slits simultaneously and interfering with itself. This wasn't simply a practical limitation of measurement technique or an artifact of crude detectors. It represented something profound and deeply disturbing about reality itself. The universe didn't have a definite trajectory for the electron until someone looked at it. The act of looking determined what they would find. This seemed to violate common sense. How could merely observing something change what it does? What kind of physical reality could behave this way? This question haunted physicists throughout the 20th century. Photons showed identical behavior with equal troubling implications. They exhibited wave properties like diffraction and interference in double-slit experiments, but also particle properties like having definite energy and momentum in photoelectric effects. Light was both and neither depending on how you measured it. This wave-particle duality seemed to strike at the heart of reality itself, attacking the very logic by which humans understood existence. How could something be fundamentally both? How could the same electron be a wave in one experiment and a particle in another? The classical picture of nature as made of definite objects in definite locations dissolved under quantum scrutiny. Nature couldn't be broken down into independent pieces and studied in isolation as classical science assumed. The properties of quantum systems depended on how you measured them. You couldn't take a measurement to determine if an electron was a wave without changing its subsequent behavior. The act of measurement created reality. At quantum scales, reality became slippery, context-dependent, fundamentally ambiguous, until measurement forced it into a definite state. Young physicists working on the problem found this deeply disturbing, but increasingly accepted it as how nature actually worked. Older physicists found it incomprehensible and often rejected it, insisting it must represent temporary confusion that future research would resolve. Yet the mathematics worked perfectly without exception across countless experiments. Every experiment confirmed it beyond doubt. The universe at small scales operated according to wave-particle duality as a fundamental principle more basic than particles or waves themselves. Nothing was purely wave or purely particle. Everything was both, expressing one aspect or the other depending on experimental context. This contextuality meant that quantum properties weren't predetermined. They emerged through interaction with measurement apparatus. This would become central to understanding quantum mechanics and what the State Postulate meant. Werner Heisenberg derived what became the most philosophically troubling result of quantum mechanics, a result that challenged not just physics, but the very nature of knowledge itself. The uncertainty principle stated that you could not simultaneously know the position and momentum of a particle with perfect precision under any circumstances whatsoever. The more precisely you determined position, the less precisely you could know momentum, and vice versa without exception. The product of position uncertainty and momentum uncertainty had a minimum value set by Planck's constant divided by 4 pi. This minimum couldn't be avoided or overcome through better instruments or more clever measurement techniques. This wasn't a practical limitation of measurement instruments. This was a fundamental principle built into the mathematical structure of quantum mechanics itself. Given any quantum state, the uncertainties in position and momentum must obey Heisenberg's inequality. This principle violated intuition at the deepest level. In classical physics, a particle had a definite position and momentum at every instant in time. These were intrinsic properties of the particle itself, existing independently of whether anyone measured them. Uncertainty emerged only from our practical ignorance or from limitations of measurement instruments. But quantum mechanics asserted something completely different. In quantum mechanics, the uncertainty was fundamental and unavoidable. The particle simply didn't have definite simultaneous values for position and momentum. This wasn't an expression of human ignorance. It was a statement about the nature of reality itself. Heisenberg showed through detailed analysis that attempts to measure position precisely required interactions that necessarily disturbed momentum fundamentally and unavoidably. To detect a particle's exact location, you had to bounce something off it to locate it, typically photons serving as probes. Higher energy photons gave better position resolution because shorter wavelengths allowed more precise localization down to smaller distances. But higher energy photons transferred more momentum to the particle, leaving the particle's momentum uncertain afterward. Lower energy photons disturbed momentum less because they transferred less energy upon collision. But low energy means long wavelengths, which give poor position resolution. You simply can't use long wavelengths to localize something precisely. You couldn't measure around this trade-off by using different measuring devices or more careful experimental techniques. This wasn't a failure of experimental ingenuity. It was woven into the fabric of reality itself at the quantum level. The trade-off existed in the mathematics of quantum mechanics. Any attempt to avoid it would violate the Schrödinger equation and contradict quantum mechanics predictions, which were confirmed by every experiment ever performed. Einstein objected strenuously to this conclusion with all the authority his towering reputation could muster. He famously declared that God doesn't play dice with the universe, expressing profound discomfort with fundamental randomness. His objection captured something deep and ancient about human desires for rational understanding. Determinism represented an ancient human hope that reality followed comprehensible rules, that knowledge of present conditions could yield perfect knowledge of the future through mathematical calculation. If the universe was truly probabilistic at fundamental levels, perfect prediction became impossible even in principle. You couldn't know initial conditions precisely enough to predict future outcomes with certainty because the universe wouldn't have initial conditions to predict from. Reality would be indeterminate at the quantum level. Einstein believed this represented incomplete knowledge rather than fundamental randomness in nature. He proposed that hidden variables, additional properties of reality we couldn't yet measure or perceive, determined quantum behavior completely and deterministically underneath the apparent randomness. If we knew the hidden variables along with the quantum state, quantum mechanics' apparent randomness would vanish like morning mist, revealing underlying determinism. Einstein hoped to restore the classical worldview where reality had definite properties independent of observation. He couldn't accept that the universe was fundamentally indeterminate. But decades of research showed that no hidden variable theory could reproduce quantum mechanical predictions in all experimental contexts consistently. John Bell developed inequalities that any hidden variable theory must satisfy if reality followed classical principles underneath. Experiments carefully designed to test Bell's inequalities violated them decisively. Experiments violating Bell's inequalities proved that no local hidden variable theory could explain quantum phenomena unless non-locality existed. Nature appeared to be genuinely probabilistic at fundamental levels. Either reality was probabilistic or it was non-local with distant correlations influencing particles instantaneously. Both possibilities disturbed physicists profoundly. The universe was either random or it was spooky with action at a distance that seemed to violate special relativity's prohibition on faster-than-light communication. Heisenberg's uncertainty principle represented a fundamental truth about reality, not a limitation of knowledge or measurement ability. The universe genuinely didn't have definite simultaneous values for conjugate properties like position and momentum. This wasn't frustrating human ignorance about what was really there. This was how reality operated at quantum scales. The State Postulate emerged as quantum mechanics' attempt to describe this fundamentally strange reality. The quantum state specified everything that could be specified about a system, but what it specified was probability distributions over possible measurement outcomes, not definite values existing before measurement. The state was complete in the sense that nothing more could be known in principle. Yet it predicted genuine randomness in measurement outcomes. This seemed paradoxical to classical sensibilities. How could something be completely specified yet random? The answer lay in accepting that reality at quantum scales was fundamentally probabilistic. The quantum state was a complete specification of a probability distribution, not a complete specification of an objective predetermined reality. Measurement didn't reveal what was there all along. It generated outcomes according to probabilities encoded in the quantum state. Knowledge transformed fundamentally from knowing facts about reality to knowing probability distributions for possible measurement outcomes. This represented the final death of classical determinism and the birth of quantum indeterminacy as fundamental features of reality itself. The universe wasn't a collection of facts waiting to be discovered. It was a collection of possibilities waiting to be actualized through measurement. The state postulate formalized this revolutionary conception. A quantum state was complete because it specified everything that could be specified. It couldn't specify more than probability distributions because reality at quantum scales didn't have more specific properties to specify. The electron didn't have a definite position before measurement. It had a probability distribution of possible positions. This wasn't a limitation of physics. This was what reality fundamentally was. This insight transformed physics from the study of what is into the study of what could possibly be and the probabilities governing which possibility gets actualized. This revolutionary understanding emerged not from philosophical speculation or abstract thought experiments, but from rigorous mathematical necessity. Physicists working through the mathematical structure of quantum mechanics discovered that the formalism itself demanded this interpretation inescapably. There was no way around it. The mathematics spoke with absolute clarity, unambiguous and inescapable in its implications for how reality must work. A quantum state captured everything knowable about a system in a mathematical object that specified probability distributions over all possible measurement outcomes. The state was complete, yet it predicted uncertainty and randomness as fundamental features of nature rather than temporary limitations of human knowledge. This seemed paradoxical, almost logically impossible at first glance, until physicists accepted that reality at quantum scales genuinely contained this indeterminacy as a basic feature woven into the fabric of existence itself. The universe didn't hide its properties from us through lack of sufficiently precise measurements. The properties simply didn't exist in a definite form until measurement forced them into being. This wasn't a problem with our instruments or our techniques. This was a statement about what the universe fundamentally was at the smallest scales. The state postulate emerged as the most radical assertion in the history of physics. It claimed that the quantum state provided a complete description of a system. Complete meant nothing more could be known in principle, but what the state specified wasn't what classical physicists meant by complete description. The state didn't specify definite values for all observable properties. The state specified probabilities. The mathematics didn't allow anything else. You couldn't force it to specify more definite information. The structure of quantum mechanics simply didn't work that way. The superposition principle, the uncertainty relations, the eigenvalue equations all combined to prevent any quantum state from specifying definite values for all observables simultaneously. The state postulate accepted this as fundamental truth rather than temporary limitation. It transformed the meaning of what a complete physical description meant. A complete description of a quantum system meant knowing the wave function, knowing the probability amplitudes for all possible outcomes of all possible measurements. It didn't mean knowing what the measurement would yield before performing it. It meant knowing the distribution of probabilities for different outcomes. This was maximally complete knowledge. You couldn't know more. The universe itself didn't contain more information than what the quantum state specified. Understanding what a quantum state actually was required abandoning classical intuitions completely and irreversibly. In classical physics, the state of a system meant something concrete, tangible, and absolutely definite. It meant knowing the position and velocity of every particle, every degree of freedom, every relevant property. These quantities existed as objective facts about the system, facts that were true and existed whether anyone measured them or not, whether anyone even knew about them or not. Classical states were complete descriptions of objective reality independent of any observer. A classical state told you everything that was true about the system. You could read off exact values for every observable property with perfect precision if you knew the state precisely. The TEM had a definite temperature existing at that moment, definite energy value that it genuinely possessed, definite momentum that truly characterized its motion, everything existing as facts, independent of observation and independent of whether anyone cared about them. You could specify the classical state at time zero and then calculate the entire future trajectory of the system through time using Newton's laws or Hamilton's equations. Every moment in the future was determined by the state and the laws of motion. Every moment in the past was equally determined. Classical mechanics was fundamentally deterministic and objective. Quantum states operated completely differently, in ways that seemed almost incomprehensible at first encounter, and remained philosophically troubling even after decades of analysis. A quantum state didn't tell you the definite values of observables that the system genuinely possessed. Instead, it specified something much stranger and more abstract. It specified a rule for calculating probabilities for different measurement outcomes. When you performed a measurement on a quantum system described by a particular state, the measurement outcome would be random, genuinely unpredictable, drawn from a probability distribution determined by the state. Different measurements on identically prepared systems starting in the same quantum state would yield different results according to the probabilities specified by the state. You could prepare 100 electrons in identical quantum states and get 100 different measured positions. No two measurements would be identical. This wasn't because the electrons were different. It wasn't because the apparatus varied. It was because quantum mechanics was fundamentally probabilistic. Before measurement, the system didn't have a definite value for the observable being measured. It existed in a superposition of possibilities. After measurement, it did have a definite value as a result of the measurement interaction. Measurement transformed possibility into actuality, potential into realized fact. This was the revolutionary core of quantum mechanics. The quantum state was a mathematical object called a wave function, typically represented by the Greek letter psi, and written as a function defined across all possible values of position or momentum or any other observable property. For a particle, the wave function specified the probability amplitude for finding the particle at each possible location in space. The probability amplitude wasn't the same as probability itself. The amplitude was a complex number, meaning it contained imaginary numbers and could be represented as an arrow pointing in a particular direction in complex number space. The amplitude could have magnitude and phase. Squaring the absolute value of the amplitude at each location gave the probability of finding the particle there. This mathematical structure meant that different locations could have amplitudes pointing in different directions in complex space. The directions of those arrows mattered tremendously for interference effects and other quantum phenomena. When two amplitudes pointing in similar directions added together, they created constructive interference. When they pointed in opposite directions, they created destructive interference. These phase relationships between amplitudes at different locations were crucial to quantum mechanics and had no analogue in classical probability theory. The wave function contained all information needed to calculate probability distributions for any observable you might measure on the system. Position probabilities came from the wave function evaluated in position space. Momentum probabilities required transforming the wave function into momentum space through a mathematical operation called a Fourier transform. Energy probabilities required yet another mathematical representation altogether. The same quantum state could be expressed in different mathematical forms corresponding to different observables, but all these forms contained identical information expressed in different mathematical languages or bases. The state was more abstract than any classical state could ever be. It wasn't a picture of how things actually were right now at this moment. It was a specification of how things could possibly be after measurement, with probability weights for each possibility. Yet this abstract, probabilistic specification was complete. It contained everything that could be known in principle about the system. More information couldn't exist and couldn't be specified because more information would require specifying definite values for observables that didn't have definite values until measurement actually occurred. The quantum state was complete in its own terms, complete in the only way that quantum mechanics allowed anything to be complete. It was just that its completeness meant something totally different from classical completeness. Rather than knowing all facts about the system, completeness meant knowing all probabilities for possible facts. Rather than definite truth, it meant knowing all possible truths with their respective likelihoods. This abstract specification required a special mathematical space to exist in, a space unlike anything that appeared in classical physics and fundamentally unlike the three-dimensional space where we live our everyday lives. Physicists discovered they could only represent quantum states consistently and self-consistently by working in an abstract mathematical space called Hilbert space, named after mathematician David Hilbert, who developed the mathematical framework in the late 19th century. This wasn't ordinary three-dimensional space where objects could be located. It wasn't even four-dimensional space-time where events could be plotted. Hilbert space was an abstract mathematical construction with infinitely many dimensions, one dimension for each possible outcome of any observable measurement on the system. The space was abstract in the sense that its points didn't correspond to physical locations. Instead, they represented quantum states. Directions in Hilbert space represented superpositions. The geometry of Hilbert space embodied the logic of quantum mechanics. A particle's quantum state required a different Hilbert space than an atom's quantum state, or a system of many particles bound together. The dimensionality of the relevant Hilbert space scaled with the system's complexity in profound ways. For a single particle, you needed infinitely many dimensions to represent all possible position values, because position could take any real number on the number line. You needed infinitely many other dimensions to represent all possible momentum values. For two particles, the dimensionality increased enormously because you now had dimensions corresponding to all combinations of both particles' properties, creating a multidimensional space that seemed impossibly abstract to contemplate. For a system of many particles, the dimensionality became so vast that the Hilbert space was utterly incomprehensible to human intuition. Yet this vast abstract space was real, mathematically, and captured everything quantum mechanics needed to say about the system. Hilbert space was the stage on which quantum mechanics played out entirely. It was the mathematical arena where quantum phenomena occurred. Physical observables corresponded to mathematical operators acting within this abstract space, transforming vectors representing quantum states into other vectors. The allowed measurement outcomes corresponded to specific mathematical objects called eigenvalues, special numbers that the operator could produce under specific conditions. The states where you could measure a definite value for an observable without any randomness corresponded to specific directions in Hilbert space called eigenstates, special quantum states that were intimately connected to the operator. These mathematical structures weren't arbitrary choices that physicists made for convenience. They emerged necessarily and inescapably from requiring that quantum theory be self-consistent, that measurements be possible, and that calculations match experimental results. The mathematics demanded this structure to make sense of experimental results and to preserve the principles of quantum mechanics consistently across all measurements and all systems. There was no freedom to choose alternative structures without destroying the entire theory. An operator in this abstract space represented an observable like position or momentum or energy or angular momentum. When you applied the operator to a quantum state, you didn't necessarily get back something simple and easy to interpret. Quantum states were linear superpositions of eigenstates of various operators, combinations of the special states weighted by coefficients. Applying an operator to a superposition could yield a mixture of different outcomes. But when you measured the observable corresponding to that operator on a quantum system, you always got a definite result emerging from the superposition. The measurement always yielded one of the eigenvalues of the operator, one of the special numbers associated with that operator. Which eigenvalue you got depended on the quantum state and the relative weights of different eigenstates in the superposition. The probabilities were determined by how the state overlapped with each eigenstate, calculated through an inner product operation in Hilbert space that quantified the overlap. After measurement, the quantum state collapsed from the superposition to the eigenstate corresponding to the measured eigenvalue. The subsequent behavior of the system then evolved according to the Schrödinger equation applied to that new state. The Schrödinger equation governed how quantum states evolved deterministically between measurements. The connection between operators and eigenvalues proved absolutely central to understanding quantum mechanics and remained philosophically profound even after physicists grew comfortable with the mathematics. The Hermitian operators, a special class of mathematical operators with particular symmetry properties that made them self-adjoint, represented observables that could actually be measured in principle. The eigenvalues of Hermitian operators were always real numbers, a mathematical fact that matched perfectly with the experimental reality that measurements always yielded real numbers. The eigenstates formed a complete basis for the space, meaning any quantum state whatsoever could be expressed as a superposition of eigenstates of a given operator. This mathematical structure guaranteed that any measurement would yield one of the eigenvalues. There could never be a measurement result that wasn't an eigenvalue. The eigenstate-eigenvalue link was more than mathematical convenience and elegant structure. It was the bridge connecting abstract quantum states to concrete measurement outcomes, translating from pure mathematics to experimental reality. When a quantum system was in an eigenstate of an operator, measuring the corresponding observable would definitely yield the eigenvalue with probability 1. There would be no randomness in the measurement outcome whatsoever. You would know the measurement result before performing it with absolute certainty. These special states represented maximum knowledge about a particular observable, knowledge as complete as quantum mechanics allowed within its framework. But achieving maximum knowledge about one observable necessarily meant losing all knowledge about other observables due to the uncertainty principle woven into Hilbert space geometry at the deepest mathematical level. An eigenstate of the position operator had no definite momentum whatsoever, containing zero component of any definite momentum eigenstate. It was spread out over all possible momentum values uniformly. An eigenstate of the momentum operator had no definite position whatsoever, distributed equally across all positions in space with no preference for any location. You could prepare a quantum system in the laboratory to have a definite value for one observable through careful measurement and selection, but this necessarily destroyed any definiteness for other observables that were incompatible with the first according to the uncertainty relations. The incompatibility came from the mathematical structure of Hilbert space and the commutation relations between operators. It wasn't a limitation that better experiments could overcome, or that future technology could avoid. It was fundamental to the nature of quantum reality itself, written into the mathematics that described all quantum systems without exception. Commutation relations between operators encoded the uncertainty principle mathematically with perfect precision. Two operators commuted if applying them in either order produced the same result. For commuting operators, the order of application didn't matter. Position and momentum operators did not commute with each other. Applying the momentum operator, then the position operator gave a different result than applying position, then momentum. The difference between these two outcomes was directly related to Planck's constant. This non-commutativity between position and momentum operators encoded the uncertainty principle precisely and mathematically rigorously. You couldn't simultaneously diagonalize both position and momentum operators. You couldn't find a single basis or representation where both were simultaneously diagonal. You had to choose one basis or the other. You had to choose which observable to know precisely and accept ignorance about the other. This choice was forced by the mathematics, not by experimental limitations. It wasn't an optional limitation that could be overcome with better apparatus. The Hilbert space formalism made it absolutely mandatory and inescapable. The mathematical structure itself prevented simultaneous knowledge of incompatible observables. Other pairs of observables commuted with each other. Position observables at different times commuted. Different components of angular momentum didn't commute with each other. Energy and momentum could have compatible measurement sequences in some systems and incompatible sequences in others, depending on the Hamiltonian operator governing the system. The commutation relations determined which observables could have simultaneous definite values and which ones couldn't. These mathematical relationships translated directly into physical possibilities and impossibilities for measurement outcomes and quantum states. Two observables with non-zero commutation relation couldn't be simultaneously measured to arbitrary precision. The product of uncertainties had to exceed the minimum set by the commutator divided by 2. This wasn't approximate or asymptotic, it was exact for all quantum states. There existed no quantum state with arbitrarily small position and momentum uncertainty. The trade-off was built into the foundations of quantum reality. Understanding these constraints proved essential for the proper interpretation of the state postulate. The state postulate claimed completeness, but completeness now meant something specific. It meant knowing probability distributions for all observables and all measurements. It didn't mean knowing definite values for everything. It couldn't mean that because the mathematics prohibited simultaneous definite values for incompatible observables. Complete knowledge in quantum mechanics meant knowing the projection of the state onto all possible eigenstates of all possible operators. It meant knowing the probability amplitude for finding any eigenvalue when measuring any observable. It meant knowing the coefficients in every possible basis expansion of the wave function. This was maximally complete knowledge. You couldn't know more without violating the laws of quantum mechanics. If you somehow had more information about definite values for incompatible observables, that state would contradict the mathematics of quantum mechanics and couldn't be a valid quantum state. Most quantum states weren't eigenstates of any particular observable, they were superpositions, linear combinations of eigenstates with different weights or amplitudes. These superpositions represented genuine mixtures of multiple possible outcomes. This distinction between eigenstates and general superpositions was crucial to understanding how quantum mechanics worked. In Hilbert space, Hermitian operators represented physical observables that could be measured. Position had an associated operator, momentum had an operator, energy had an operator, angular momentum had operators for each component. These operators acted on quantum states, transforming them according to mathematical rules. When you applied an observable's operator to an eigenstate of that observable, you got back the eigenstate multiplied by its eigenvalue. This multiplication by a number was the key property that defined eigenstates and eigenvalues. An eigenstate was the special quantum state, such that the operator acting on it produced back the same state scaled by a number, the eigenvalue. This simple mathematical relationship carried profound physical meaning. It meant that for that special quantum state, the observable had a definite value equal to the eigenvalue. No superposition, no uncertainty, no probability distribution, just a definite fact. For any Hermitian operator representing a physical observable, you could find a complete set of eigenstates that spanned all of Hilbert space. These eigenstates formed an orthonormal basis, meaning they were perpendicular to each other in the geometric sense of Hilbert space and normalized to unit magnitude. Every quantum state, no matter how complicated, could be expressed as a superposition of these eigenstates with appropriate coefficients. The coefficients determined the probability distribution for measurement outcomes. The system in such a superposition would yield different eigenvalues depending on which eigenstate the superposition collapsed to upon measurement. The probabilities came from squaring the amplitudes of the coefficients. This structure explained why measurements always yielded eigenvalues. When you measured an observable on a quantum system in any state, the system collapsed to one of the eigenstates of the measurement operator. You got back the eigenvalue corresponding to that eigenstate. Which eigenstate you got depended probabilistically on the state before measurement. The probabilities came from how much of each eigenstate was present in the superposition. A state with equal parts of two eigenstates had equal probability for getting either eigenvalue. A state with mostly one eigenstate and a small component of another would give mostly the first eigenvalue with occasional instances of the second eigenvalue. The representation of quantum states in different bases corresponded to expressing the state in terms of different sets of eigenstates. Position representation expressed the state as a wave function in position space, specifying the probability amplitude for finding the particle at each location. Momentum representation expressed it as a wave function in momentum space, specifying the probability amplitude for each possible momentum value. energy representation expressed it in terms of energy eigenstates, decomposing the state into contributions from definite energy levels. These different representations contained identical information, but expressed it differently mathematically in different mathematical languages. The same physical quantum state had different mathematical forms in different representations and different bases. Converting between representations required mathematical transformations like Fourier transforms, but the underlying physics and the predictions for all possible measurements remained identical. This basis independence of quantum mechanics meant that no particular basis or representation was more fundamental than another. Reality didn't prefer position or momentum or energy. The quantum state existed abstractly in Hilbert space, independent of how you chose to represent it mathematically. The abstract state in Hilbert space was the fundamental reality. All specific representations were merely mathematical choices for convenience. The State Postulate asserted that complete knowledge of this abstract quantum state in Hilbert space constituted complete physical knowledge. You couldn't know more than the state provided without running into contradictions with the structure of quantum mechanics itself. If you somehow had information about specific values for incompatible observables simultaneously, that information would be inconsistent with the state and therefore impossible to reconcile with quantum mechanics predictions for all other measurements. The State Postulate was the endpoint of centuries of thought about the nature of physical knowledge. It claimed that true completeness didn't mean knowing definite values for everything. It meant knowing probability distributions across the space of all possibilities. It meant accepting that reality was fundamentally probabilistic and indeterminate at quantum scales. This represented the end of classical determinism and the beginning of a new era where probability was fundamental rather than derivative from hidden deterministic variables. Superposition was the most disturbing and philosophically troubling feature of quantum mechanics, more troubling even than randomness or uncertainty principles, more alien than probabilistic wave functions that seemed unintuitive but at least describable. Superposition meant that a quantum system could exist in multiple distinct states simultaneously until measured and collapsed by interaction with measurement apparatus. An electron could be in multiple locations at the same time, occupying several positions in space without being smeared out or distributed or probabilistically somewhere or other. The electron was actually in both places in the superposition state. An atom could be in multiple energy levels at the same time, existing in several definite states of excitation simultaneously as a coherent superposition. A photon could have multiple polarizations at the same time, being both vertically and horizontally polarized without being an incoherent classical mixture of randomly polarized photons. The coherence of the superposition was crucial. Different components interfered with each other through their phase relationships. The superposition was qualitatively different from classical probability distributions. This wasn't because of measurement limitations or imperfect apparatus or noise or our incomplete knowledge about which single state the system actually occupied. The system genuinely existed in multiple states at once. It wasn't that the electron was really in one location and we just didn't know which one. The electron wasn't in any single location. The superposition was a real feature of the quantum state, not merely our ignorance or an artifact of our measuring procedures. The superposition was how reality actually existed before measurement disturbed it. This represented a fundamental statement about the nature of existence at quantum scales. Reality at small scales was inherently multiple and indefinite until measurement actualized particular outcomes. The double-slit experiment illustrated superposition most clearly and compellingly and had become the quintessential demonstration of quantum mechanics' most alien feature. An electron fired toward a barrier with two slits passed through both slits simultaneously as a superposition of two paths. It didn't take one path or the other, with some definite but unknown probability. It took both paths at once, going through slit A and slit B simultaneously, interfering with itself like a wave passing through multiple openings and creating interference patterns. The interference pattern proved beyond doubt that the electron followed both paths simultaneously. It created regions on the detector screen where the two paths amplified each other through constructive interference, building up strong signals, and regions where they cancelled through destructive interference, producing darkness and zero probability. The pattern couldn't be explained if the electron chose one slit or the other randomly according to classical probability. Only when you installed a detector to measure which slit the electron passed through did everything change fundamentally. Then the electron took a definite path. If the detector recorded passage through slit A, no interference pattern appeared. If it recorded slit B, no pattern. Only when you didn't measure and left the slits unobserved did the interference pattern return, indicating the electron somehow went through both slits simultaneously as a superposition. The act of measurement forced the electron into a definite path, destroying the superposition completely. Before measurement, the electron existed in superposition of multiple paths, genuinely in both locations. After measurement, it took a definite path, one or the other. The measurement changed the physical system fundamentally through wave function collapse. This violated every intuition about how physical objects should behave in space and time that humans had developed through interaction with the everyday macroscopic world. Objects in classical physics shouldn't be in multiple places at once. They should have definite locations at each moment. They should follow definite trajectories through space and time, one path from beginning to end, traceable and predictable. Superposition represented a genuine and profound departure from this classical expectation and common sense intuition. The mathematics of quantum mechanics required accepting this alien feature as fundamental and completely inescapable. There was no way to reformulate quantum mechanics to eliminate superposition without destroying the entire theory and losing agreement with all experimental predictions. Every attempt to preserve determinism and single-path trajectories while keeping quantum mechanics predictions led to contradictions or worse, experimental agreement. Superposition was non-negotiable, a core feature of reality at quantum scales. Superposition combined with the probabilistic interpretation of measurement to create a theory where reality was fundamentally indeterminate and multiple until measurement occurred and actualized definite outcomes. The universe was fundamentally made of possibilities, not facts, until someone looked. Before measurement, the electron didn't have a definite location in space. It existed as a superposition of locations weighted by probability amplitudes that could add and subtract through interference. After measurement, it had a definite location drawn from the probability distribution. The act of measurement selected one possibility from the superposition of many possibilities and actualized it into reality. The wave function collapsed. The superposition transformed into a definite eigenstate. This transformation of possibility into actuality through measurement represented something radically new in physics, something that had never appeared in scientific thought before quantum mechanics forced the issue. Classical physics never required possibility to become actuality through some external process like measurement. Everything always was actual, whether measured or not, whether anyone knew about it or not. Objects had definite positions. Particles had definite velocities. The future was determined by initial conditions and laws of motion. Quantum mechanics made the opposite assertion that contradicted classical worldview in every way. The universe at quantum scales existed as superpositions of possibilities until measurement forced actualization. This meant that the act of measurement created facts about the universe that didn't exist before measurement occurred. The measured value wasn't revealed through the measurement. The measurement didn't simply disclose a pre-existing fact. The measurement generated it according to probability rules encoded in the quantum state. Measurement created reality rather than revealing it. This responsibility of measurement for creating facts about the world seemed almost impossible to accept. It violated the objectivist belief that facts existed independently of observers. Yet every careful mathematical analysis of quantum mechanics led inexorably to this conclusion about the role of measurement. The mathematics simply demanded it inescapably. The experiments confirmed it beyond doubt. There was no escape from this conclusion. The universe at quantum scales operated according to principles where superposition was real and fundamental, where measurement created reality rather than revealing it, where probability and possibility were fundamental aspects of existence. This was how nature actually worked at the deepest level, in the quantum realm beneath classical approximations. The State Postulate formalized these revolutionary insights and radical principles into a complete mathematical framework that captured all of quantum mechanics consistently and precisely and without exception. A quantum state was everything that could possibly be specified about a system. It was complete in the sense that nothing more could be specified in principle without violating the fundamental structure of quantum mechanics. Yet it was indeterminate about specific concrete observable values for most observables in the state. It specified probability distributions for outcomes of all possible measurements. The state evolved deterministically according to the Schrödinger equation when no measurement occurred, following mathematical equations as precise and deterministic as Newton's laws of motion. Upon measurement, it collapsed instantaneously to an eigenstate of the measured observable, selected according to probabilities determined by the state before measurement. These principles defined quantum mechanics completely and governed every quantum system without exception. These principles also redefined what knowledge meant, what reality was, what truth signified, and what role observation played in the fabric of existence itself. Reality was no longer assumed to be objective and independent of observation, existing as solid facts whether anyone looked or not. Reality emerged through interaction between quantum systems and measuring apparatus. The universe wasn't a collection of facts waiting passively to be discovered by passive observation and measurement. The universe was a collection of possibilities and potentialities waiting to be actualized through measurement and interaction. The State Postulate made this revolutionary picture mathematically rigorous and absolutely precise. Every quantum system in the entire universe was described completely by its wave function or state vector in Hilbert space. Every measurement performed on any quantum system corresponded to an operator. Every possible measurement outcome was an eigenvalue of that operator. Every probability for different outcomes came from the overlap between the state and the eigenstates of the measured observable. This framework left no ambiguity about how to calculate predictions. The State Postulate was the foundation of quantum mechanics, the fundamental principle from which everything else followed logically. Understanding it required abandoning centuries-old classical intuitions about reality, knowledge, and the passive role of observers. The universe wasn't a stage where facts existed independent of observers. The universe was a participatory reality where observers and observed were entangled. But once you accepted this revolutionary picture, quantum mechanics became clear and beautiful and powerful beyond measure. It captured all of reality at quantum scales perfectly and completely. The deepest practical challenge in quantum mechanics emerges the moment you ask the fundamental question that links theory to reality. How do abstract quantum states describing infinite possibilities collapse into the definite, singular results we actually observe in laboratories when we measure quantum systems? This is the measurement problem, the core puzzle that has haunted quantum mechanics since Niels Bohr and Werner Heisenberg first grappled with its implications in the 1920s. The measurement problem isn't a technical difficulty awaiting solution through better mathematics or clever experimental refinement. It's a conceptual crisis that strikes at the heart of what quantum mechanics actually means about the nature of reality itself. Before any measurement occurs, the quantum system exists in superposition, a mathematical object in Hilbert space encoding probability amplitudes for infinite possible outcomes. The superposition is real. The system genuinely occupies multiple states simultaneously in the quantum description. But the moment you perform a measurement, something profound happens that the mathematical formalism cannot fully explain. The superposition collapses into a single, definite outcome. The infinite possibilities crystallize into one actuality. The mathematics predicts the probability distribution over possible outcomes with perfect precision, but which outcome actually occurs in any particular measurement remains fundamentally random, subject only to the probabilistic rules encoded in the quantum state. The measurement problem asks how this dramatic transformation from possibility to actuality actually occurs. What physical process causes the collapse? Is it instantaneous, or does it take finite time? Does the collapse occur in the measuring apparatus, in the quantum system itself, or in the mind of the observer? The problem is that the Schrödinger equation, which governs how quantum states evolve, doesn't predict any collapse whatsoever. The equation describes smooth, continuous, deterministic evolution of the wave function through time. Applied to the combined system of the quantum object plus the measuring apparatus, the Schrödinger equation yields an even larger superposition, not a collapse to a definite outcome. The equation entangles the quantum system with the apparatus in increasingly complex ways, never producing the sharp, definite measurement results we actually observe. If the Schrödinger equation is the complete and correct description of all physical processes, then wave function collapse cannot occur. Yet, empirically, measurements always produce definite outcomes. They never produce superpositions of outcomes. The universe is far too cooperative with human experimental desires to leave measurements in indefinite superpositions. The measurement always yields a number, a fact, a definite result. The Schrödinger equation apparently fails to describe this fundamental aspect of quantum mechanics. This represents a massive inconsistency at the core of the theory. Consider a concrete example to grasp the severity of this problem. An electron exists in a superposition of being at two different locations simultaneously, say location A and location B, with equal probability amplitudes. You construct an apparatus designed to detect the electron. The apparatus involves a detector at location A and another detector at location B. When you switch on the apparatus, the electron must interact with it through electromagnetic forces and quantum fields. According to the Schrödinger equation, the electron's superposition state becomes entangled with the detector's states. If the electron was at location A, the detector at A gets activated. If at location B, the detector at B activates. But the Schrödinger equation doesn't produce a situation where one or the other detector fires. It produces a superposition of both detector firing scenarios occurring simultaneously. The entanglement creates a larger combined state spanning the electron plus both detectors in complex superposition. This is not what happens experimentally. Experimentally, exactly one detector fires. Only one outcome occurs. The other detector remains silent. Yet the mathematics of the Schrödinger equation applied to this system yields superposition of multiple outcomes, not the single definite result observed. This failure of the Schrödinger equation to predict definite measurement outcomes represents the core of the measurement problem and the most fundamental crack in the foundation of quantum mechanics. As a complete theory of nature, the Copenhagen interpretation, developed by Bohr and Heisenberg and their colleagues, attempted to resolve the measurement problem by introducing collapse as a fundamental principle beyond the Schrödinger equation. When a measurement occurs, the Copenhagen interpretation asserts the wave function collapses into an eigenstate of the measured observable. The collapse is not derived from deeper principles. The collapse is postulated as a basic feature of how quantum mechanics works. This is where the reduction postulate or projection postulate appears, a fundamental addition to the quantum mechanical formalism that sits alongside the state postulate. The reduction postulate says that when measurement of an observable occurs on a system in a superposition of eigenstates, the state instantaneous usly collapses to one of those eigenstates. The probability of collapsing to each eigenstate equals the squared amplitude of that eigenstate's coefficient in the superposition. After collapse, subsequent measurements of the same observable on the post-measurement state yield the same result with certainty because the state is now an eigenstate of that observable. The reduction postulate solves the measurement problem practically and pragmatically. It lets physicists calculate correct predictions for all experimental results. It lets them design apparatus and predict outcomes with stunning accuracy. It works in practice even though it introduces fundamental inconsistency into the formalism. The Schrödinger equation governs evolution between measurements. Collapse governs the instantaneous change during measurement. These two principles contradict each other fundamentally. The Schrödinger equation is deterministic and smooth. Collapse is stochastic and instantaneous, yet both are apparently necessary to describe quantum reality completely. This embedded inconsistency bothered many physicists deeply. Einstein famously rejected it, insisting that quantum mechanics was incomplete and that hidden variables must exist beneath the probabilistic surface. Schrödinger developed his famous cat thought experiment partly to express his dissatisfaction with collapse. If a quantum system in superposition could somehow affect a macroscopic object like a cat, making it both alive and dead simultaneously, then collapse must occur at some point to restore our everyday experience where cats are definitely alive or definitely dead, never both. But where does collapse occur? When the superposition affects the cat? When we look at the cat? When the cat becomes conscious? The thought experiment revealed that Copenhagen was philosophically unsatisfying despite being empirically successful. The interpretation declares that the division between microscopic quantum systems and macroscopic classical apparatus is crucial and fundamental. The quantum system before measurement exists in superposition. The measuring apparatus is assumed to be fundamentally classical, not described by quantum mechanics. The apparatus definitely occupies some classical state. When the quantum system interacts with the classical apparatus during measurement, the superposition collapses, but this raises immediate questions. Why is the apparatus classical? By what principle should we exclude the apparatus from quantum mechanical description? The apparatus consists of atoms and electrons, fundamentally quantum objects. There's no clear dividing line between quantum and classical. In practice, physicists approximate the apparatus as classical when it's macroscopic enough that quantum effects become negligible through environmental decoherence. But this is an approximation, not a fundamental division. The approximation works well in laboratories where measuring apparatus is far too large to display obvious quantum behavior, yet in principle the apparatus should be described quantum mechanically too. Then collapse must occur at some other point in the chain. Some physicists propose that consciousness might trigger collapse. When a conscious observer looks at the result of measurement, the superposition collapses into the observed outcome. This seems even more philosophically problematic than the apparatus distinction. It gives consciousness a role in collapsing wave functions, suggesting that reality depends on minds observing it. It raises questions about whether animals are conscious enough to cause collapse. What about plants or microbes? At what level of consciousness does collapse occur? The observer interpretation became notorious for its apparent mysticism disguised as physics. John von Neumann developed mathematical formalisms exploring the chain of measurements extending back to a conscious observer. He showed that the mathematics is consistent regardless of where you place the boundary between system and apparatus, as long as you place it somewhere before conscious observation occurs. This suggested that the boundary location is arbitrary, which seemed to strengthen arguments for consciousness causing collapse. But it also suggested that consciousness might not be necessary at all, that some other boundary would work equally well. The ambiguity and arbitrariness of the measurement boundary became recognized as a fundamental weakness of the Copenhagen interpretation. The collapse of the wave function represents perhaps the strangest feature of quantum mechanics, and certainly the most philosophically disturbing. It introduces discontinuity into physics, where the Schrödinger equation had promised smooth evolution. It introduces randomness, where determinism governs everything else. It introduces the role of observation as fundamental to physical process rather than passive and neutral. Before collapse, the quantum state specifies probability distributions. After collapse, the state specifies definite values for the measured observable. Between measurements, the state evolves smoothly according to the Schrödinger equation, changing continuously as time progresses. Upon measurement, the state jumps discontinuously to an eigenstate. The jump is instantaneous, no time interval elapses, no finite process describes the transition from superposition to eigenstate. It's not like the state gradually concentrated its amplitude into one eigenstate over microseconds or nanoseconds. The transition is genuinely instantaneous. The amplitude was distributed across all eigenstates one moment, then localized entirely in one eigenstate the next moment. The other amplitudes simply vanished. They didn't go somewhere else. They didn't transform into something else. They ceased to exist because the superposition no longer applied. The state after measurement was entirely different, a fundamentally new quantum state rather than a modification of the old state. This instantaneous jump struck Einstein as impossible, leading him to his famous declaration that God doesn't play dice and that quantum mechanics was incomplete. How could a distant quantum system instantaneously transform its state without any physical signal traveling to it and affecting it? Einstein believed this violated the principle that no signal could travel faster than light. He argued that the instantaneous correlation between measurement and collapse implied that quantum mechanics couldn't be the complete theory of nature. Something deeper, some hidden variable or additional hidden information, must govern quantum systems. Einstein's philosophical objection proved mathematically incorrect through Bell's theorem and subsequent experiments, as will be discussed. But his intuition about the strangeness of instantaneous collapse remained valid. Collapse is strange. Collapse is problematic philosophically. Collapse violates principles physicists held sacred like locality and determinism. Yet collapse is empirically necessary to connect quantum theory to observable reality. The mathematical description of collapse captures the essential features empirically but provides no mechanism explaining how it occurs. When a particle's position eigenstate projection operator acts on the superposition state, it selects the component corresponding to the measured outcome. The projection operation mathematically filters the superposition, extracting one component and normalizing it to unit magnitude to create the new post-measurement state. This mathematical operation works perfectly for calculating what happens after measurement. But it doesn't explain what physically happens during the collapse process. The mathematics describes the outcome, but not the process producing that outcome. Physicists working in different interpretations of quantum mechanics proposed entirely different physical pictures for how collapse might actually occur. Objective collapse theories proposed that the wave function undergoes spontaneous collapse without any measurement apparatus required, triggered randomly according to dynamics built into the Schrödinger equation itself. These theories modify quantum mechanics at its foundations to include collapse mechanisms independent of measurement. The many worlds interpretation proposed that collapse never occurs at all. Instead, the wave function continues evolving smoothly according to the Schrödinger equation everywhere. Every measurement outcome that could occur actually does occur, creating branching realities. We experience only one branch, the one in which the measurement yielded the particular outcome we observed. Other versions of ourselves in other branches observe different outcomes. This eliminates the measurement problem by eliminating collapse entirely through radical reinterpretation of what measurement means and what reality consists of. The information theoretic approach proposed that the wave function isn't describing fundamental reality, but only our information about reality. Collapse represents updating information when measurement reveals previously unknown facts. This interpretation accepts collapse, but claims it represents learning rather than physical transformation. Each interpretation handles the measurement problem differently, yet all reproduce quantum mechanics experimental predictions perfectly. This multiplicity of interpretations, each successfully describing the same physics, is itself philosophically troubling. It suggests that the underlying reality might be inaccessible to our observations and measurements in ways that transcend experiment. The relational interpretation proposed that properties don't belong to systems in themselves, but only exist relative to measurement interactions. A particle doesn't have an intrinsic position except relative to a measuring apparatus that couples with it. This completely shifts the philosophical ground of quantum mechanics away from properties of independent systems toward relational properties that emerge through interaction. The relational view aligns with the State Postulate in suggesting that the quantum state is primary and concrete properties are derivative. Rather than objects existing with definite properties that measurements reveal, measurements create the properties through relational coupling with quantum systems. The Born rule emerged from Max Born's interpretation of the wave function and remains perhaps the most fundamental connection between mathematical quantum states and physical measurement outcomes. Born suggested that the wave function's absolute value squared gave the probability density for finding the particle at each location if position measurement were performed. This simple rule transformed the wave function from a mysterious mathematical object into something with direct physical meaning and empirical consequence. The Born rule states that if a quantum system is in a superposition of eigenstates with coefficients C1, C2, C3, and so on, then the probability of measuring the eigenvalue corresponding to eigenstate I equals the absolute value of Ci squared. The probability is the absolute value of Ci squared. For a position wave function, the Born rule says that the probability of finding the particle in a small region of space equals the wave function squared in that region. If the wave function is large, at location x and small at location y, you're much more likely to find the particle near x than near y when you measure its position. The Born rule is beautifully simple and empirically perfect. Every prediction quantum mechanics makes for experimental results flows from applying the Born rule to calculate probabilities. Experiments verify these predictions with accuracy approaching 1 part in a trillion in some cases. The Born rule works. The Born rule works so reliably that physicists rarely question it anymore. But the Born rule's empirical success doesn't answer what it actually means. Why should squaring the amplitude give probability? Why does the square of a complex number represent likelihood for finding something at a location? What is the physical meaning of the wave function that makes this rule true? These questions remain philosophically unanswered and arguably unanswerable. The Born rule is empirically verified, but conceptually mysterious. It connects the abstract mathematics of Hilbert space to the concrete probabilities observed in laboratories. This connection is somehow correct, somehow perfectly mapping mathematical amplitudes to physical frequencies. The rule works without requiring deeper explanation or justification. Nature apparently follows this rule simply because that's how quantum systems behave. The Born rule could have been different. Nature could have followed a different rule connecting amplitudes to probabilities. But this is the rule that nature actually obeys, whether for reasons we can fathom or reasons forever beyond our understanding. The deep mystery of the Born rule becomes apparent when you consider what the wave function actually represents physically. Is the wave function a real thing that exists in ordinary three-dimensional space? Is it a mathematical fiction that only appears real through the averaging of many measurements? Is it fundamentally defined in the abstract Hilbert space of all possible quantum states rather than in physical space? Different interpretations of quantum mechanics give completely different answers to these questions. Realists about the wave function view it as representing something physically real, perhaps a field permeating all of space or a fundamental aspect of reality. Anti-realists view the wave function as merely a mathematical tool for predicting measurement outcomes without necessarily corresponding to anything real. Instrumentalist interpretations regard quantum mechanics as purely a predictive device, making no claims about what reality actually is beyond what we can measure. Yet all these interpretations use the Born rule identically. They all square the amplitude to get probability. They all produce identical predictions for all possible experiments. The Born rule remains valid regardless of what philosophical interpretation you do you adopt about what the wave function means. This suggests that the Born rule expresses something deeply true about how nature works at the quantum level, something that transcends philosophical debates about the nature of quantum reality. The Born rule's universality across all interpretations points toward a deeper principle that might explain it, though no such principle has been discovered despite decades of effort by leading physicists and mathematicians. Some have speculated that the Born rule might emerge from more fundamental principles once quantum mechanics is incorporated into a theory of quantum gravity or quantum cosmology. Others suspect that the Born rule might be so fundamental that it cannot be derived from anything deeper, representing an axiom of nature rather than a derivable consequence. The practical implementation of the Born rule in experimental quantum mechanics involves preparing systems in known quantum states, performing measurements and collecting statistics on outcomes over many repeated trials. If you prepare 1,000 electrons in the same initial quantum state and measure a particular observable on each one, the distribution of measured values will match the probability distribution predicted by the Born rule applied to that state. Quantum mechanics never predicts individual outcomes, only the statistical distribution across many repetitions. This distinction between predicting individuals' outcomes versus predicting statistical distributions represents a fundamental aspect of quantum mechanics. Each individual measurement contains randomness that cannot be predicted. The Born rule predicts only the aggregate behavior. When physicists design quantum experiments, they must account for this inherent randomness. They cannot trust any single measurement outcome. They must perform repeated measurements and analyze statistical patterns. Modern quantum experiments often involve millions or billions of measurements to establish statistical significance and verify quantum mechanical predictions to high precision. The power of the Born rule lies in its ability to make statistical predictions with perfect accuracy, even though individual outcomes remain unpredictable. Entanglement represents the most alien consequence of quantum superposition and the most direct challenge to classical intuitions about separability and independence of distant systems. When quantum systems interact or are created together, their quantum states can become correlated in ways that have no classical analog or explanation. Two particles can be created together such that measuring a property of one particle instantaneously determines what measurement of the same property on the distant partner particle will yield, even if the particles are light years apart. This spooky action at a distance, as Einstein called it in his famous critique, represents a correlation so tight and so instantaneous that it seems to require faster-than-light communication between the particles. Yet measuring one particle doesn't send a signal that reaches the other particle. The particles don't communicate. The correlation emerges from their shared quantum state, their entanglement, encoded in the wave function describing both particles together as a single system in Hilbert space. Entanglement occurs when the wave function of two particles cannot be factored into separate parts describing each particle independently. The joint wave function is fundamentally indivisible. Neither particle has a definite state on its own. The state is defined only for the pair together. If you measure the first particle's spin and find it pointing up, the second particle's spin will necessarily point down, correlated perfectly with the first. But before measurement, neither particle has definite spin direction. Both exist in superposition. The measurement on the first particle determines the second particle's state instantaneously, regardless of separation distance. Einstein found this philosophically intolerable. He believed that physical reality had to be local, meaning distant systems couldn't influence each other instantaneously. He believed reality had to be real, meaning properties of systems had to exist prior to measurement rather than being created by measurement. He argued that quantum mechanics violated both locality and realism, and therefore couldn't be the complete theory of nature. Hidden variables must exist, Einstein asserted, governing the particle's properties in advance and ensuring locality. If hidden variables determined the spin directions in advance, then there would be nothing mysterious about measurement. The correlation would exist because both particles had predetermined spins from their creation. Measurement would simply reveal these pre-existing values. There would be no spooky action or violation of locality. Hidden variable theories could preserve both realism and locality while reproducing all quantum mechanical predictions. Einstein's proposal seemed philosophically satisfying and mathematically possible, but John Bell proved mathematically that hidden variable theories could not simultaneously satisfy certain constraints without contradicting experimental predictions. Any hidden variable theory that preserved locality and realism would make predictions for certain measurements that differed from quantum mechanical predictions. Bell constructed an inequality that any local realistic hidden variable theory must satisfy. Quantum mechanics predicts violations of this inequality under specific measurement configurations. Experiments performed those measurements and found violations of Bell's inequality exactly as quantum mechanics predicted. This proved that hidden variable theories couldn't work. No hidden variable theory could reproduce quantum mechanical predictions while maintaining both locality and realism. Something had to give. Quantum mechanics preserved agreement with experiments while sacrificing either locality or realism, or both. Most physicists concluded that realism had to be abandoned, that properties don't exist prior to measurement. Some argued that locality had to be violated, that measurement of one entangled particle instantaneously affected the distant partner, regardless of distance. Both conclusions seemed almost impossible to accept. Yet experiments repeatedly confirmed that entanglement was real, that correlations between distant particles were genuine, that quantum superposition and entanglement represented fundamental features of nature rather than artifacts of measurement or incomplete theory. The practical applications of entanglement, once dismissed as philosophical curiosity, have become central to developing quantum computers and quantum cryptography systems. If quantum states could be entangled and manipulated precisely, information could be processed using quantum parallelism unavailable to classical computers. Multiple possible answers could be explored simultaneously through quantum superposition, then collapsed to the correct answer through careful measurement. Quantum teleportation could transfer quantum states through entanglement without sending physical particles themselves. Quantum key distribution could use entanglement to create unbreakable encryption codes detectable to eavesdropping attempts. The engineering challenges to harness entanglement remained formidable, but the fundamental physics demonstrated that entanglement was real and usable. This transformation of entanglement from philosophical embarrassment to technological resource marked a shift in how physicists viewed quantum mechanics. What seemed impossible according to intuition proved essential according to mathematics and experiment. What struck Einstein as an unacceptable violation of locality became accepted as fundamental to quantum reality. The state postulate applies to real quantum systems in laboratories and in nature with the same mathematical precision that it applies to idealized theoretical systems. When an electron with unknown spin is prepared in the lab and you measure its spin, the quantum state specifies probability distributions for both possible outcomes. Each outcome is equally likely in an unprepared electron with unknown spin. After measurement, the state collapses to a definite spin state, either spin up or spin down. If you measure the same electron again immediately afterward, you get the same result with certainty. The electron's state is now a spin eigenstate. If you measure a different component of spin at an angle to the first measurement, the quantum state predicts a new probability distribution dependent on the angle between measurement directions. The state postulate describes all these phenomena with mathematical precision and empirical correctness. In atomic systems, electrons in atoms occupy quantum states describing orbital shapes and energy levels specified by quantum numbers. The state of a multi-electron atom specifies the quantum state for each electron in superpositions of orbitals and energy levels, coupled together through their electrostatic interactions. The quantum state predicts probability distributions for finding electrons at different distances and angles from the nucleus. The state predicts allowed energy values that electrons can possess. When the atom absorbs a photon of specific energy, the electron's state collapses to a higher energy eigenstate. When the atom emits a photon, an electron transitions from a higher energy state to a lower one, releasing energy as light. The spectral lines we observe from excited atoms emerge directly from the state postulate applied to atomic quantum states. In molecular systems, electrons are shared between nuclei through entangled quantum states forming chemical bonds. The bond strength and character emerge from the quantum state, describing where electrons are most likely to be found between the nuclei. Different molecular geometries arise from different electronic quantum states, different superpositions of orbitals that the electrons occupy. Chemical reactions occur when quantum states of reactant molecules rearrange into quantum states of product molecules through the interaction of their electron clouds. The state postulate describes all chemical phenomena perfectly. In particle physics, the state postulate extends to relativistic quantum fields, fields that pervade all space and can create and destroy particles. The quantum state of an electromagnetic field specifies the probability distribution for finding different numbers of photons at different energies. The state postulate applied to quantum fields predicts emission and absorption of photons by atoms and molecules with extraordinary precision. It predicts the spectrum of the cosmic microwave background radiation. It predicts particle creation in high-energy physics, energy collisions. The state postulate works across every scale and every system without exception or limitation. Quantum states with complex structures apply to macroscopic systems like crystals containing trillions of atoms with electrons occupying collective quantum states called energy bands that determine electrical conductivity and other properties. These energy bands emerge from the quantum states of electrons shared across many atoms, creating patterns of allowed and forbidden energies that govern whether materials conduct electricity or insulate. Superconductors exhibit quantum states where electrons flow without resistance through entangled pair states called Cooper pairs that occupy a single macroscopic quantum state. These Cooper pairs condense into a collective quantum state, where all pairs occupy identical quantum numbers, creating the famous zero-resistance flow characteristic of superconductivity. Superfluids exhibit quantum states where the entire liquid flows without viscosity as a single coherent quantum entity. Helium-4, cooled to temperatures near absolute zero, exhibits this superfluid behavior where macroscopic portions of the liquid act as a single quantum entity defying all friction. Laser light consists of photons in identical quantum states, a macroscopic manifestation of quantum superposition where trillions of photons are coherently in the same state, producing behavior impossible for ordinary incoherent light. The coherence and monochromaticity of laser light emerges from the quantum state where photons occupy the same quantum mode, sharing identical wavelength and phase relationships. The state postulate scales from single particles to macroscopic systems seamlessly and uniformly. Its predictions match experimental reality across orders of magnitude in size and complexity. The state postulate is not merely an abstract mathematical principle, it is the accurate description of how nature actually works at every level, from subatomic particles to macroscopic systems to the cosmos itself. Every quantum phenomenon, every particle interaction, every atomic transition, every chemical reaction, every molecular property that we observe in our experience of physical reality emerges from the state postulate. Understanding the state postulate means understanding the fundamental basis of all quantum mechanical phenomena. It means recognizing that reality is fundamentally probabilistic and indeterminate at quantum scales. It means accepting that observation and measurement play roles in actualizing reality that classical physics never imagined necessary. It means acknowledging that the mathematical formalism of quantum mechanics in Hilbert space captures something profound and true about the nature of existence itself, something that transcends our everyday classical intuitions and our comfortable assumptions about how reality must work. The state postulate provides a bridge between the abstract mathematics that describes quantum systems and the concrete reality of experimental measurements and physical phenomena. Without the state postulate, quantum mechanics would be merely a sophisticated mathematical game with no connection to actual reality. With the state postulate, quantum mechanics becomes a framework for understanding how nature genuinely operates at its deepest levels. The postulate asserts that the quantum state is everything, that it provides complete knowledge within the bounds of physical possibility, that it determines all outcomes probabilistically. The postulate also implies that there exist aspects of reality we can never know with certainty, that indeterminacy and probability are features of nature rather than limitations of our knowledge. This acceptance of fundamental uncertainty in physical reality represents one of the greatest intellectual achievements of 20th century science. The state postulate is the culmination of the quantum revolution in physics that transformed our understanding of nature from a deterministic machine following fixed laws to a participatory cosmos where observers and observed are fundamentally entangled.